Hey there! If you're about to step into a chemistry lab, then this is for you. We're going to break down the essentials of measurement, units, and the one thing that trips up just about everybody, significant figures. All right, let's get into it. So, I want to start with a quick story. There was a student, probably a lot like you, who turned in a lab report they were super proud of. They'd used their calculator for every single step and wrote down every single number that popped up on the screen. They figured, hey, more numbers means I'm more accurate, right? Well, when they got that report back, it was just covered in red ink. And the instructor's point was pretty simple. Your calculator has no idea how precise your tools are, but you have to. And this whole explainer, it's all about making sure that never, ever happens to you. So, to avoid that sea of red ink, we first got to get on the same page with the universal language of science. And that all starts with units and prefixes. And that language is called the SI system. It's the international standard that scientists use everywhere. It means a gram in a lab in Ohio is the exact same as a gram in a lab in Tokyo. It's the bedrock of all our measurements. Okay, let's look at the building blocks you'll be using all the time. We've got meters for length, seconds for time. Now, for mass, here's a little heads up. The official SI unit is the kilogram, but in the lab, we're almost always going to be working with grams. And of course, the mole, which is just so important in chemistry for counting tiny things like atoms. But what if you're measuring something that's really, really big or super, super tiny? Well, that's where prefixes come in to save the day. They're just multipliers. Kilo means 1,000 times bigger, milli means 1,000 times smaller. Oh, and don't get thrown off by those little negative exponents. All that means is that it's a fraction. It's just a super handy scientific shorthand. All right, so we've got the language down. Now let's get back to the real reason we're here, figuring out how to count the digits that actually matter. This is what we call significant figures, or sig figs for short. Okay, so there are rules. You gotta know them. Any number that isn't a zero, always significant. Easy enough. Zeros stuck in the middle, like in 4.062, they're sandwiched in, so they're always significant too. The tricky ones are the zeros at the ends. A zero at the end only counts if there's a decimal point somewhere in that number. See how 5.60 has 3 sig figs, but 560 has only 2? That little dot, it changes everything. Okay, pop quiz. Let's see if you got it. How many significant figures are in 901 grams? Think about where that zero is. Yep, it's 3. That zero is a sandwich zero. It's trapped between the 9 and the 1, so it absolutely has to count. All right, let's try another one that's a little bit trickier. What about 80.0 milliliters? Pay very close attention to that decimal point. And that's 3 again. Because there's a decimal point, those zeros at the end aren't just placeholders. They're actually telling you that your measurement was precise all the way to that decimal place. Okay, so counting them is one thing, but the real test, the place where most of that red ink comes from, is using them in calculations. So let's break down the 2 critical rules you absolutely have to know. Now this is probably the single most important thing to get right. There are 2 different rules. When you multiply and divide, it's all about the total number of sig figs. But when you add or subtract, you completely ignore the total count and you look only at the number of digits past the decimal point. Mixing these 2 up is the #1 mistake. Okay, let's try a multiplication and division problem. We've got 3 different measurements here. Which one is our weakest link? Which one has the fewest significant figures? It's got to be the 0.98, right? It only has 2 sig figs, and that's our limit. So no matter what crazy long number your calculator spits out, our final answer is only allowed to have 2 sig figs. So we have to round that whole thing to just 4.5. Remember, you're only as precise as your least precise measurement. Now for addition. And remember, new problem, new rule. We are not counting total sig figs. Forget about it. We're only looking at the decimal places. So which of these numbers is the least precise in that regard? It's 560. It has 0 digits after the decimal point. That means our final answer has to have 0 digits after the decimal too. So even though the calculator gives us 565.292, we have to round that to the nearest whole number. The correct answer is 565. Okay, we've got the rules for counting, and we've got the rules for calculating. Now let's put it all together into a simple, repeatable method for solving problems with precision. Here it is, 4 easy steps. First, identify what you're given and what you're trying to find. Second, plan out what conversion factors you need.
Third, set up the problem so that your units cancel out. And finally, the last step, do the math and then round to the correct number of sig figs. Let's see it in action. So, here's a nice, straightforward conversion. We need to convert 1.91 meters into centimeters.
Okay, so we start with what we're given, 1.91 meters. That has 3 sig figs. Now, our conversion factor, 100 centimeters in 1 meter, that's a definition. It's an exact number, which means it has infinite significant figures, so it's not going to limit our precision. The only thing that limits us is our original measurement. So we started with 3 sig figs. Our answer has to have 3 sig figs, 191 centimeters.
And that brings us right back to where we started. This is the single most important takeaway. Your calculator is just a tool. You are the scientist. You are the one who has to tell the calculator's answer what the rules of precision are. So the next time you're in the lab and your calculator gives you a long string of numbers like this, you'll know exactly what to do. The question isn't just what's the answer. The real question is, based on my actual measurements, how many of those digits can I really, truly trust?